This is a pre-class video on module 3 symmetrical components. In this video I will be explaining the sequence impedance and sequence networks. Myself Dr. M. J. Chandrasekhar, Associate Professor, Department of EEE, SJB Institute of Technology. This is session 2. In session 1 on symmetrical component, I explained what are symmetrical components, how to understand the positive sequence component with phasor diagram, negative sequence component, zero sequence component, and the operator A and the relation between the positive, negative and zero sequence component, how to express the unbalanced phase voltages or unbalanced phase currents in terms of its symmetrical component of voltages and currents. And also I explained the complex power in terms of symmetrical components. Today in this video we will be understanding the sequence impedances and sequence network. What do you mean by the sequence impedances? There are three sequence impedances: positive sequence impedance, negative sequence impedance and zero sequence impedance. So, what is zero sequence impedance? It is the per phase impedance of a symmetrical three phase star connected impedance offered to zero sequence current producing zero sequence voltage. Similarly, that can be represented like Z naught. This is zero sequence component. Then positive sequence component is the positive sequence impedance is the per phase impedance of a symmetrical three phase star connected impedance offered to positive sequence current producing positive sequence voltage, and the negative sequence impedance is the per phase impedance of a symmetrical three phase star connected impedance offered to negative sequence current producing negative sequence voltage. So, what do you the difference between sequence impedances and sequence network? These sequence networks are formed using the sequence impedances. When only positive sequence currents are present, the impedance is positive sequence impedance. Similarly, the negative sequence currents are present, then the impedance is called negative sequence impedance, and zero sequence impedance is the one in which the zero sequence currents are present in the impedance, then that impedance is zero sequence impedance. So, the reactance diagram formed by using the zero sequence impedances are called zero sequence impedance, and the reactance diagram formed by using negative sequence impedance is called negative sequence network, and the reactance diagram formed using zero sequence impedance is called zero sequence network. So, this is the difference between the sequence impedances and sequence networks. Next, we will see one of the important derivation on sequence impedances. So, sequence impedance of the transmission line, let us consider the sequence impedance of the transmission lines. So, here here I have considered the three transmission lines, that is A, B and C. There are the three line currents are flowing in the lines A, B, C. They are IA, IB and IC are the line currents are flowing in the transmission line. The phase voltage between the line and the reference is VA, and similarly VB and VC are the phase voltages, and the neutral current is given by IA plus IB plus IC is the neutral current, and each of the lines, let us consider the reactance of the series line, that is phase A and phase B, phase C. Let us assume they are all symmetrical. That means, what are the characteristics which we get in phase A will be there in phase B and phase C. So, the reactances of all the three lines will be same, and the effect of one line on the other is also same, that is Xm is the mutual reactance of any pair. So, the derivation heading may be like this. See, here we have to prove the analysis using symmetrical component is advantageous only in symmetrical systems, or the question may be to prove that in a symmetrical system the quantities of different sequences do not react upon each other, or the question may be to prove that in a three-phase circuit with equal self and mutual impedances, and it is different from Z0. That means here Z1 is equal to Z2 and it is different from Z0. So, we have to prove this. So, by seeing this static load also we will consider. Static load means the load value remains same with respect to time. The voltage current relation for this circuit, let us write the VA is the phase voltage, VA is equal to IA into ZS XS plus IB into XM plus IC into XM. Similarly, we can write the equation for VB and VC. VB is IA into XM plus IB into XS plus IC into XM. Here IA into XS, XM mutual, IB into XM plus IC into XS. Because if you consider one circuit, that is this circuit closed path, KVL you can apply, the applied voltage VA is equal to drop, that is IA into XS, and this effect is there XM, and this XM will be there. So, that is why we have to consider IB into XM plus IC into X. So, this is how we can write the expression for the phase voltages. It is shown here. The next slide is shown. The KVL equation, it can be written like this. So, the difference in voltage is VA, that can be written as, these are the mutual, this is self, XS, XS and XS. So, this we can write from the given. So, the same equation you can write in matrix form. This is VA, this is VA, this is VA dash, then these are the reactance constant and IA, IB, AC. You can easily write that matrix equation. Let us write the equations in matrix notation. Matrix notation, that is V phase minus V phase dash is equal to Z into IP. So, we know that the V phase is tau PS into Vs. That means here we have phase voltages like VA, VB, VC, and the constant matrix in terms of A or alpha, that is 1, 1, 1, 1, 1, 1, A square, A, 1, A square. This I explained in the previous session. Here the symmetrical components, you can write this, that is the symmetrical component of Vs. The Vs values are Va0, Va1, Va2. This is how we can write these are the phase voltages. This is tau PS into Vs. Here tau PS is also you can write as A into Vs. So, here also A into Z is there, IP is nothing but A into IS. So, this can be written as here A inverse Z into A. So, this can be, first let us calculate what is A inverse Z into A. A inverse is nothing but this is A, that is 1 1 1 1 A square A 1 A square A, then A inverse is nothing but 1/3 of 1 1 1 1 A square 1 A square A. So, A is known, A square is known, Z is known. So, take this A dash, A inverse Z and A matrix, multiply the 3 matrices, we will get this answer. It is shown here that positive and negative sequence reactances are same and it is different from this. So, let us understand this in the next slide. Here this is in terms of symmetrical components it is written. So, this is written in matrix form and this is the first diagonal element is Z1, second diagonal element is Z2 and the last one is Z0. So, I0, I1, I2, I0. See, this is Z1 is called positive sequence impedance and negative sequence impedance and zero sequence impedance. It is proved here that positive and negative sequence reactances are same and it is different from the zero sequence impedance. So, here it is shown in these figures how to represent the transmission line positive sequence impedance, negative sequence impedance and the zero sequence impedance. This positive sequence impedance involves, we will get the positive sequence network. Here only the positive sequence voltage and currents will present. So, the applied voltage is V1 and the current flowing through the transmission line is I1 and it has positive sequence impedance and the terminal voltage is V1 dash. Similarly, the negative sequence network is formed by negative sequence current flowing in the impedance, negative sequence impedance. So, here also V2 I2 and the terminals voltages are V2 and V2 dash. Similarly, the zero sequence network is formed by having the current in the zero sequence impedance. Next, we will understand how to write the positive, negative and zero sequence impedances for different power system elements. So, let us consider generator, how to write positive, negative and zero sequence impedance. Similarly, if you consider the transformer, how to write these positive, negative and zero sequence for different configurations of the transformer windings. Transformer windings may be connected in star fashion, delta fashion or star delta, delta star, like this we have many combination, and how to represent the positive, negative and zero sequence impedances for load. And in the previous slide I have shown that how to write the positive, negative and zero sequence impedance for transmission lines. Okay, next we will consider the positive and negative and zero sequence network representation for the synchronous machine. Unloaded synchronous machine is grounded through the reactor. See here, we have considered the equivalent circuit of the 3-phase generator. Each phase, see here, this is each phase, first phase, that is A phase. A phase is represented by its induced voltage along with the reactance of the A phase winding, and similarly B phase and C phase, and it is all the 3 phases are connected in star fashion and neutral is grounded through the reactance. If this is the circuit for which how to write the positive sequence, the neutral current is nothing but the currents which are generator, basically it is the currents are going out of the windings, IA, IB, IC are going out. then the neutral current will be the algebraic sum of the 3 line currents. Now, let us see how to write the positive sequence network for the synchronous machine. Here the synchronous machine, it is considered 3 phase 3 wire, and in each phase the parameters are same, that is EA, EB, EC source voltages. They are equal in magnitude and phase spread by 120 degree, and Z1 is the positive sequence impedance, and its equivalent circuit is referred as like in reactance diagram what we write for one line diagram. Similarly, here also it is written the source voltage, that is in each phase what are the parameters are there, that is represented here as positive sequence network. And whereas this the terminal voltage, we can write the expression for the voltage VA1 is nothing but EA minus IA1 Z1, because source voltage is more. So, that is EA is equal to terminal voltage plus IA1 Z1. So, it is understand that the source is causing the terminal voltage and the drop. Therefore, this equation. Next, we will see the negative sequence network and impedances for the negative sequence network. See here, in the negative sequence network, we are not considered the source, rest of all the things are same. Even in the 3 phase model, we are not considered the sources. Sources are there in the only positive sequence, negative sequence we do not consider. This is the negative sequence impedance Z2, and its network is like this. This is the negative sequence network of a generator. Similarly, we can write the zero sequence impedance and network. This is the zero sequence impedance. I will write this put together. This is put together is zero sequence impedance. This zero sequence impedance, it has 2 terms. One is Zg0 and 3 times of Zn. Why? Because from neutral to ground, neutral to the phase A, if you see the total impedance, that is Zg0 and Zn, and this path is carrying the current 3 times of Ia0. Therefore, it is 3 is considered here, Ia0 is here. So, that voltage is Va0 is equal to minus 3 times of Zn minus 3 times of Zg0 here. So, this is the formula for the terminal voltage Va0. Here the zero sequence impedance is the sum of 3 times of Zn plus Zg0. So, if you write the zero sequence network for the synchronous machine, if we neutral only star connection means you have to show the open circuit. Suppose if it is grounded solidly, then we should consider only the equivalent circuit like this. And if you are considering delta, then again open circuit we have to show like this. And suppose if the neutral is grounded through reactance, then one more reactance like this it comes apart from that. So, this is how we can write the zero sequence network for the synchronous generator, and the synchronous generator windings are connected in whether it is star fashion or star neutral grounded through reactance, or the windings are connected in delta fashion. So, based on the winding connections, we can write the zero sequence network. Next, we will see the writing of the sequence network for the transformers. The transformer in which the transformer windings I will write transformer here. if you consider the transformer, here the positive and negative sequence impedances are written as series impedance, just like in transmission line, positive and negative sequence impedance. That is Z1 and Z2 are represented as series impedance, just like in transmission line. So, this is VA1 and this is IA1. Similarly, here VA2 and IA2. But zero sequence impedance are written based on the winding connection of the transformer. Suppose if you take two winding transformer of this kind, two winding transformer, the windings of the primary and the secondary in a three phase basis, they may be connected in different fashion, star star, star delta, delta star, star delta, star grounded, like this many combinations. There are 9 combinations we can make. So, for all these different winding connections of primary and secondary winding, let us understand how to write the zero sequence network. Zero sequence network. Now, you see the transformer winding connections. Here it is star fashion, here star is grounded. Then the zero sequence network for this type is here star connection, this is zero sequence network, neutral is grounded. Like this we can write the zero sequence network for star, star grounded. This is the equivalent circuit of zero sequence network. This is the winding connection. Here star and here star is neutral grounded, and here zero sequence current, if you want to write for the transformer, we have to consider the assumptions. What are the assumptions we do here is, the magnetizing current is neglected and the primary winding will carry the current only if there is a current flow in the secondary winding. Primary winding will carry current only if there is a path provided. Here there is no path provided in this, because neutral current cannot flow, there is neutral wire is absent here, but here provision. But the question here is, the primary winding will carry current only if there is a path provided in the secondary winding. Similarly, the secondary winding will carry current only if there is a path provided in the primary winding. There is no path here, therefore the equivalent circuit is open circuit. This is how we can write the X naught of a given transformer with this connection. Next we will see one more we will see the transformer in star star fashion. If this is the case, then the primary winding, it won't have any option of carrying the neutral current, this neutral wire is absent, here neutral wire is present, but path should provide in both the things. Therefore, the zero sequence network like this, it is shown here. Similarly, the star star connection, if there is only star star, that is, this is star neutral grounded and here is also star neutral grounded. That means primary winding and secondary winding, there is a provision to carry the current. Therefore, the equivalent circuit is like this. So, X naught or the Z naught. Next, we will see how to write the zero sequence network for the star delta transformer. This star neutral is grounded and delta. So, here the provision of zero sequence current can flow in lines as well as the phases. Therefore, we can write like this, but secondary lines are not carrying current, but phases will carry current. This is how we can write the zero sequence network for the star grounded delta. Star grounded delta. Next, we will see how to write for delta delta. As you see here, it is 3-phase 3-wire delta fashion. Zero sequence current can flow in the phases. Therefore, you can write this is this is star not delta. This is star, this is delta. But zero sequence current cannot flow in the star, only 3 wires. Therefore, it can be written as open circuit. This is Z naught. Next, we will see how to write the zero sequence network for delta delta. Delta delta. So, here 3-phase 3-wire, here also 3-phase 3-wire. So, here there is a provision of current to flow in the phases. Therefore, this can be written as delta means always you write open circuit, but it carry phases, not in the lines zero sequence current flows. This is the equivalent circuit for the delta delta connected transformer bank. Next, we will see the construction of sequence network of the given system. Similarly, there are many types of winding connections like star grounded, star, again star grounded, and then delta, star, star grounded, delta, and delta, star grounded. So, there are totally this many combinations, 2, 4, 6, 7, 8, 9 combinations are there. So, just I will write how to write the zero sequence here, zero sequence network like this, here zero sequence network like this, here delta means open, here you can write like this, this is a zero sequence network, here you can write this is the zero sequence network, here is also zero sequence network like this, then here zero sequence network like this, because here neutral current can flow in both these primary and secondary, therefore, and here is also delta. This is how here zero sequence current can flow in the one phase. See here zero sequence current flow, here in phases it will flow. Similarly, here neutral current flows. So, this is how we can write for various combination of the transformer windings, we can write the zero sequence network. So, with this I will be ending this video. So, I will recap the video what I did. So, in this video I explained one derivation on positive and negative sequence impedances are same and it is different from positive and negative sequence impedance in case of symmetrical 3-phase transmission line. In a 3-phase symmetrical transmission line with equal self and mutual values, we have proved that. Thereafter, we understood the concept of sequence impedances and sequence networks, and I explained how to write the sequence impedance and sequence network for generator, transformer and transmission line. With this, I will be ending this video. Thank you.